Section 3.4 Measures of Relative Standing. Have you ever taken a standardized test such as the ACT, SAT, GRE, or a professional exam? If you have, in addition to your score, you were given a percentile. If you scored in, say, the 85th percentile, although we've worked with finding the sample mean and sample standard deviation S, those values can easily
be skewed by very large or very small numbers. We saw that with our small company data. Another way to look at data is using percentiles. Percentiles tell us about the position and the equal being approximate depending on the size of the data set. But percentiles means out of 100, so it gets divided into 100 equal groups. To find the percentile rank of a data value x, we do the following. Take the number of values that are less than x, the value you're interested in, divide by the total number of values, and then multiply by 100. That will give you the percentile rank. So let's take a look at example 1. The birth weight of 15 of the most recent newborn babies at New Hope Hospital are given below in pounds. Find the percentile of a newborn baby that weighed 7.5 pounds at birth. Now, before we can decide how many values are less than 7.5, we'll want to get our data values in order. So it looks like 5.4 is the smallest, a little baby. And then 5.9, 6.5, 6.6, 6.8, 7.3, and that occurs twice, 7.4, 7.5, 7.8, 8.2, 8.5, 8.7, 9.1, and let's see if we can make that a little bit better, 9.1 and 9.3. So let's locate 7.5, which is right there, and I need to count how many values are less than 7.5. Let's see what we have. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 values less than 7.5. So now to find the 8, and that gives us 53.3. So we could say a baby that weighed 7.5 pounds at birth for this particular hospital is in the 53rd percentile. Now remember, we've done this in some other sections, but I just thought I'd type it up here. Remember, you can use your calculator to sort those data values by going into Stat Edit. And there's also, if you choose to use the calculator in Alex, there's also a sort feature there, but I'm assuming a lot of students probably have the TI-84 or 83 calculator. If you don't, of course, contact the instructor. Okay, so sometimes we know, so in the previous problem, we were interested in the percentile of a specific data value, but other times we might want to know the percentile, but we want to know the data value that goes with it. So we kind of work a little bit backwards on that. So here, to find the data value that corresponds to the kth percentile, we use the following formula. So L equals N times K over 100, where L is the location of the data value after they have been sorted or ordered. Either of those words is okay. N is the total number of data values. Remember, it's the same thing as the sample size. And K is a percentile. Depending on how your answer comes out, you want to keep two things in mind. A, if L is a decimal value, the location of the data value is the next largest integer. So pretty much you're going to think of that as rounding up. B, if L is a whole number, take the average of that value and the next largest value. So we'll get a chance to see an example of those two in the next example, example 2. Refer to the data about the newborn babies. What is the value of the 10th percentile? What is the value of the 40th percentile? So what I'm asking here is, I'm interested in the 10th percentile. I want to know what weight falls in that range. So I know that N is equal to 15 because there's 15 data values in my chart. K is 10 for the 10th percentile. Now I'm going to plug all that into my formula. So 15 times 10 over 100. And that comes out to 1.5. But as mentioned, if we end up with a decimal, we want to round up to the next largest integer. So we'll round this up to 2, which means in my sorted values, I'm going to look for the second data value. So let's go back to our sorted data. And it looks like the second value is 5.9. So the baby that weighed 5.9 pounds at birth is in the 10th percentile. Okay, then we're also asked for the 40th percentile, so we'll do the same thing. N equals 15. This time K will equal 40. So that's 15 times 40 over 100. And that comes out to exactly 6. Well, this is the second case. Since we got a whole value, six and 7. Well, with this data, it just so happens that the two are the same, 7.3 and 7.3. But I'll go ahead and set it up, which means it's still just 7.3. But be sure that you don't just look, when you get a whole number, you don't just look at the 6th value or whatever that number comes out to be. Take the average of that value and the next highest one to find the percentile rate. So for this one, and just stating it a slightly different way, the value of the 40th percentile is 7.3. Okay, so percentiles divided our data into 100 equal parts. Similar to that, quartiles also tell us about the position of the data, but instead of 100 equal groups, quartiles divide the data into 4 equal groups. We're going to find quartiles pretty much the same way we found percentiles. For quartiles, we'll let K equal 25 for the first quartile. That's usually denoted Q sub 1. Let K equal 50 for the second quartile, Q sub 2, and let K equal 75 for the third quartile, Q sub 3, in the percentile formula that we've already been using. Just wanted to mention, though, that's not the only way to find quartiles. Another way is just to find 3 medians. Q2 50% is the median of all the data. It's just the middle. And then Q1 would be the median of the lower half of the data, and Q3 would be the median of the upper half of the data. And different calculators or computer programs are going to find the quartiles in different ways. Some might use the first technique we mentioned. Some might use this method of finding medians. So there is some possibility of differences in answers depending on the method that's used. But I just wanted to point that out as an alternative method. Okay, example 3. The test scores for one section of an algebra class are given below. Scores are out of 100. Find the 75th percentile. So just like before, we have to order our data. And see, our lowest value is 45, 57, and yes, of course, you can still use your calculator to sort these. Sometimes all the typing in, though, you might choose to do it by hand. 73, 83, 87, 92, and 93. Okay, so we're all ordered. The 75th percentile, if I use my formula from before, L equals, well, there's 9 data values, times 75 over 100, which equals 6.75. And because that's a decimal, we're going to round up to 7, so it's the 7th data value. So going in order, 1, 2, 3, 4, 5, 6, 7, it's going to be 87. So 87 is the 75th percentile. And if you want to, go ahead and check to see if the other method comes out the same. Sometimes it does, a lot of times it does, but every once in a while, depending on the size of the data set, it might not. It might be a little bit different. Okay, so we've learned about quartiles. And if we take quartiles together with the highest and lowest values of a data set, that's referred to as the 5-number summary. So the 2 quartiles, or the 3 quartiles, the Q1, Q2, and Q3, and then the high value and the low value, that creates the 5-number summary. The 5-number summary is used to create another type of graph called a box plot. You'll also hear this referred to as a box and whisker plot. I think that'll become obvious here in a moment. So here are the steps to constructing a box plot. Number 1, find your 5-number summary of your data. You can either do it by hand, or remember your calculator can do it as well. Then we're going to construct the box plot. To do that, draw a horizontal or vertical number line scaled to your data. Whether it's vertical or horizontal does not matter. It's just a preference and the way you like to display it. Number 3, draw a rectangle that starts at Q1 and ends at Q3. Number 4, draw a line in the box at Q2 perpendicular to the number line, so it's going to split up your rectangle, but not necessarily symmetric. And 5, put a dot at the lowest data value. Draw a line parallel to the number line connecting the lowest value in the box. Then, in the same manner, put a dot at the highest value and draw a line connecting it to the box. That might seem like a lot right now. I think once we get into an example, you'll understand kind of what all these steps are telling you to do. Okay, so here's number 4. The data below represents the value in billions of dollars of the damage of 10 hurricanes. Find the 5-number summary and IQR for this data and construct a box plot. IQR, kind of threw this in here. IQR stands for the interquartile range, and all that is the difference from Q3 to Q1. That's all that is. And we're going to find it, but we'll actually use that number in the next example. So, okay, lucky for us, our data is already sorted. That was very nice. And we need to find the 5-number summary. I'm going to go ahead and do this on the calculator. So first I need to put my list in, my data values. And I'm going to clear this out. 7, 1.9, 2.1. When you're putting your values in, make sure you don't type in extra values, and if you drop your decimal, that can really change things. So it doesn't hurt to double check that your values all look okay as you're entering them. 20.3. Okay, 10 data values. Then I go to Stat, over to Calc, one variable statistics, and I'm going to tell my calculator to run it on the first list, list 1. So remember, the information at the top is the mean and sum of x squared, and standard deviations. But if I arrow down, there's that 5-number summary sitting there for me. So the min, I'm going to go ahead and jot this down. Actually, let's do this. Okay, I'll just paste this over here to save from writing that. Okay, so we have our minimum value of 1.1, which we see right there. Q1 is 1.9, the median is 2.35, and Q3 is 6.2, and the highest value is 20.3. Okay, so remember our steps for constructing a box plot. First, I'm going to make a rectangle from Q1 to Q3. So 1.9 is just a smidge from 2. 6.2, and I'm just going to connect those and make a rectangle from Q1 to Q3. Then my median, a line for the median goes inside. So 2.35 is about here. Then I'm going to make a dot at the lowest value, 1.1, and connect it to the box. So that's kind of where the box and whiskers name comes from, because it looks like a whisker. And then the highest value way over here at 20.3, and we'll connect that. Okay, so what a box plot does is it gives us an idea of where the middle 50% of the data is. That's what this box represents. And it also tells us where a median falls within that middle 50%. And then the whiskers tell us about skewness. If you notice, that 20.3 is really pulling us way out to the right. And we might even think of that as an outlier because it's so different from all the other values that we have. And the last thing we're supposed to do is the interquartile range, which is Q3 minus Q1, or in this case would be 6.2 minus 1.9, or 4.3. So that tells us how wide the range is for that middle 50%. Okay, and one other thing I wanted to mention, we kind of mentioned it, said something about that 20.3. Let's talk a little bit about outliers, because they occur sometimes in your data. So in our previous example, we had a data value that didn't seem to fit with the other data values. And given that this is hurricane data, maybe it's something like the totals from Hurricane Katrina, being that damage was not only from the hurricane, but then the levees breaking and all the flooding that occurred. So it was not an error, it was unusual, but it's not in the regular trend of what usually goes on with hurricanes. So it's part of the data set, but it's just a very unusual data set. When you are analyzing any data, it's really important to identify outliers. Sometimes outliers can be a mistake. Somebody keyed in something wrong, or a measurement was taken accurately. In this case, it's probably a valid data point, but as we mentioned, it might just be an unusual case. But you want to identify outliers because they can potentially skew our data. So we want to make sure we know what's going on with them. With our box plot above, we got that long whisker to the right because of that 20.3, that outlier. So another way to still have a box plot and take into consideration that outlier is with a modified box plot. With a modified box plot, outliers are values that are above Q3 by more than 1.5 or 1.5 times the IQR, the interquartile range, or they're below Q1 by more than 1.5 times the interquartile range. So this is kind of a standard way to measure how far out is an outlier, because you might have an extreme value, but maybe it's not really an outlier. But if it's more than 1.5 times the measurement of the IQR, then it's definitely an outlier. When we construct a modified box plot, it pretty much looks the same, but we just kind of lose that outlier. We don't throw it away, but we just don't draw that line all the way out to it. So we'll take a look at that here. So we're still going to use the same 5-number summary. You don't throw out the value and get a whole new 5-number summary. You just modify your graph a little bit. Okay, so example 5, we're going to use the same information, and we're just going to show you what a modified box plot looks like. So we had a value at 1.1 was our min. Q1 was 1.9, so a smidge over 2, draw my line there. And Q3 at 6.2, there's our rectangle. And then put my median at 2.35. And instead of going all the way out to that 20.3, I'm going to draw my line to the next lowest value. So looking at our original data set, the value that came before 20.3 was 6.8. So 6.8, maybe about right there. And then we still acknowledge that we had that outlier by putting an asterisk or a dot by itself. So what that does is that gives us more of a realistic picture of what generally happens, the amount of damage from hurricanes. So they're mostly concentrated between, because this was in billions of dollars, between $2 and $6 billion, maybe going out to about 1 to 7 billion. But we can see that that's a little more symmetric. Whereas when we were including the 20.3, it really threw things off. So modified box plot shows you that it acknowledges the outlier here, but it just doesn't include it in the graph.